Hi, I'm Dr. Trevor from Physics This Week. Let's do a sample problem involving a inclined plane. Okay, so let's look at the problem setup. We've got a box. It has a mass of 1 kilogram, slides down a 2-meter long frictionless plane that has a height of 0.5 meters from the floor. And we want to know how fast the mass is sliding when it reaches the floor. So we draw our picture for this, put our object in, put down a couple of variables that we might find useful. And as I showed you earlier, you're going to rotate your coordinate system, draw your free body diagram with that rotated coordinate system. And then you're going to break that into components. In particular, you're going to break the gravitational force into components, which are going to be Fg perpendicular and Fg parallel. Okay, let's write down a few things that we know. Reading through the problem, we got the mass of 1 kilogram and so on down through. Notice that I have listed this as L in one place and X in another. It's going to be the same number. The X is what's going to go into the kinematics equations, and we'll replace that with L, and then eventually we'll replace it with the 2 meters. So the object starts from rest, so the initial velocity is 0 meters per second. What we don't know are the final velocity, but we also don't know the time that it takes to get to the bottom, and we don't know the particular acceleration. Now, if you remember from an earlier video, there is a way to find that, and we're going to go through Newton's second law to get that. The last thing we know is that the sine of the angle theta here can be found using H and L. That might be useful to have, and in fact, a lot of times people will actually discover that angle early and do the math to get it. I prefer not to do that. I like to keep the variable form as long as I can, because sometimes there's some hidden physics that you might find. Okay, if we look at Newton's second law in that x direction, which is down the plane, the only force that's acting is Fg parallel. So we take the vector equation into a algebraic equation, and then using a little bit of simple trigonometry, Fg sine theta is equal to mass times the acceleration. And of course, the force of gravity is just mg. And I'm using g as just positive 9.8 here. I'm not putting in any other value for it as far as the sine is concerned. The sine is already taken care of by the setup of the problem. Okay, the mass again turns out to be something that we can cancel on each side. If we have friction, that might not be the case, but for now, as long as it's sliding down frictionless, this is almost like it's in free fall down the incline, so the mass cancels out. Okay, then we go to the kinematics equations, replacing the x with L. As I mentioned earlier, the initial x position is 0, the initial v position is 0, or excuse me, the v velocity is 0, and so on. So we can simplify down a little bit. But we have an expression here for a. Now I don't have it listed as ax here, but you can see that's the only acceleration that it has, so I've just left off that subscript as we go down. I have this expression for a. I'm going to pop that in after I solve for t to get that expression. Now the reason that I'm solving for t is this equation by itself isn't sufficient to get me the final velocity. Even this equation isn't quite good enough to get there because I don't know t yet. That's why I solve for t first. Okay, so if I put in what I know, I put in my zeros. I don't put in any other number than a 0 anywhere in these equations. Okay, I've got an expression for a. I've got an expression for t. And now notice what I can do. I can throw some algebra into here. And it turns out that if I take this g sine theta inside the radical, I have to square it. Now just imagine this was the only term. If I took the square root of it, I would get my g back. That's a nice little algebraic trick that you can do to make these problems a little easier on yourself. And now I've got g squared on the top, g on the bottom, sine squared theta on the top, and sine theta on the bottom. And I can replace that by crossing those terms out or canceling on top and bottom. And now I can replace the sine theta with h over L, and then that L over L that's hidden in here simplifies out. So notice what happens here. By not putting in any other numbers than 0, I get a very simple expression that I can now put my numbers into. If I didn't, then in my calculator I would have to play around with this sine theta. There might be some rounding that's involved because of going through the sine function and then lopping a couple of digits off at the end. But now I can just put in 3 numbers. So I do that. Notice that the 2 times 0.5 gives me just 1. And now really I only have to put 1 number into my calculator. I do that, I get that out, and then I round it so that the velocity of this thing at the bottom of the incline is 3.1 meters per second. Notice the units do work out here. Up above I had a meters times a meter, which gave me the meters squared. This second squared wrote along just from the form of g earlier. And when I take the square root of meters squared per second squared, I end up with meters per second, which is the unit that I was looking for all along here. So that's a pretty good sign that I haven't done anything screwy in here and made any simple mistakes. By checking my units, I could find those. Now you might be thinking, well, there's another equation of motion that I could use. That's not this one. It's not this one, but it's the combination of those two, which doesn't involve the time. If you have this one in your pocket and you're comfortable with using it, by all means go ahead and do that. I found it helps me learn the physics a little bit better if I use these two equations. But of course, this one's going to save me a ton of time because some of the algebra that I did on the last version of this problem is already encoded into this guy. So I know my V0 is a 0. I pop that in. I know my X initial position is 0, so I pop that in. And again, I already had from earlier this g sine theta is my A, or my acceleration. So I can pop that in, and this should be starting to look familiar again. Substitute in for the sine, h over L, do some cancellation, and I've got that equation back that I had on the last page. Notice I've saved myself quite a bit of time, quite a bit of effort in doing that. Again, if you have this equation and you're comfortable with using it, by all means, go right ahead. And of course, I get the same number that I got the last time. Okay, now in a quick review of this, if you're going to solve a problem on an inclined plane, tilt the coordinate system first to point down the incline. That's going to make your life a whole lot easier. You break the gravitational force into components along this coordinate system, and this coordinate down the incline is going to be the only net force acting. From this simple problem what we just did, where it started from rest at the top and we had the incline height, then you can just write this down, or eventually you get to this point to solve it, and then pop in your numbers and get that out. Okay, again, by avoiding inserting numbers too early into the problem, we got this guy. Now, on a physics exam, you might be asked to start from the kinematics equations to get to this final point. If you do, and you have this guy memorized, you have a target to shoot for. And if you don't get to this guy, there's obviously something going on that you need to go back and fix. By fixing that, hopefully you'll get more points on your exam and build up your grade a little higher. This has been Dr. Trevor for Physics This Week. I hope this has been helpful. If this has been helpful, please give us a thumbs up or like us or subscribe. Thanks for your support.